get started, okay, we're going to get started. All right. Okay, so that was inference. That's like if you understand everything I said, you have a very good bird's eye view of the whole field of inference in graphical models. So now, let's talk about learning. So what do we mean by learning? Imagine I have a graph like this, and this graph corresponds to a factorization of the joint distribution of these 4 variables. And what do I mean by that? Well, let's now think about what each of these terms is. Each of these terms is a conditional probability of some variable given its parents. Okay? Now, assume each of the variables is discrete and can take on k sub I states. So for example, let's say x1 can take on 2 states as a binary variable, and x2 can take on 3 states it's a ternary variable like this. So then the parameter theta 2 is a 2 by 3 table where the rows sum to 1. Okay? That's all it is. So in this case, or in general, we can represent the parameters of discrete graphical models as a set of conditional probability tables with the following semantics. Table 2k prime corresponds to the table associated with the second variable, which tells you the probability that that variable takes on the value k prime, given that its parent took on the value k. And this can be slightly complicated because a node can have multiple parents, so you have an array representing this. But we can always represent this as a 2-dimensional table by simply collapsing over all exponentially many values of the parents of a node as one of the axes of the table, and then the child is the other axis. Okay, so the question of learning parameters is, given a data set of observations of the states of these variables, how do we learn these tables from the data? Okay, how do we learn the parameters theta from the data D? Well, there are different ways of doing learning. Let's just look at maximum likelihood learning to start out with. So assume you have a data set D of observation of all of these variables. We have n of these observations. We assume that they came IID from a graph with this structure. We are going to assume that the structure is fixed. And then we write down the likelihood. Because it was IID, it's a product over data points of P of the nth data point given the parameters. And then we want to maximize the likelihood, or equivalently maximize the log likelihood. The nice thing that happens when we do that is the product over n turns into a sum. And then each of these terms, because of the factorization of the graph, turns into another sum over variables. And then you get the log probability of the ith variable given its parents and the parameters of the ith variable. Okay? So basic rules of probability being applied here. Now, to do maximum likelihood learning, we want to optimize this thing as a function of each of these theta i's. Now, importantly, this log likelihood decomposes into a sum of functions of each parameter for each of the nodes. Okay? So the optimization can be done separately on each node in the graph. And if you write down the derivative of this thing with respect to theta, and you optimize it subject to the constraint that the rows of theta have to sum to 1, you get this equation. Okay? What is this equation? It says that the theta I k k prime element is n I k k prime renormalized. What is n I k k prime? N I k k prime is the number of times in the data set I've observed the variable I taking on the value k prime when its parents took on the value k. Nothing could be simpler than this. All it says is count how many times different configurations happened in your training data, fill up your tables with those counts, then normalize the rows of those tables, and you get this maximum likelihood parameter estimate. Sorry if you can't see all the way down here. I will put my slides online back when I have internet again, which will be after this. Okay. So you simply calculate the frequencies. All right, now that was easy because all the variables in my graph were observed and the structure was also known. So we can now progress up the path of more and more difficult problems. So what happens if the structure is known, but now you have hidden variables in your graph? So imagine I observe only some of the variables in my graph. Let's call those y and shade them in. And the x variables are hidden. Well, now we can still do maximum likelihood learning of this graph. We can write down the likelihood function, which is the probability of what I've observed, which is y given the parameters theta. And now something annoying happens, which is this probability of the observed data given the parameters is written as a sum over all the hidden variables of the joint probability of everything. Okay? So the cost function I'm trying to optimize is this log of a sum of configurations on this graph. Okay. Now, if I have a lot of hidden variables, this could be an exponentially big sum. But the good news is, if my graph has a sparse structure, let's say it's singly connected, I can actually do that sum efficiently by applying message passing. All right? So in general, I could compute this log likelihood and optimize it with respect to theta using any optimization method that I want. But here is a very nice and intuitive algorithm for doing that optimization, which is the EM, or expectation maximization algorithm. So raise your hand if you've studied EM in the past. Most people, this is not surprising. Some people have not. Who hasn't studied EM? Okay, a few people. Now, the EM algorithm corresponds to 2 steps iterated. In the E step, what we do is we fill in the hidden or missing variables, holding our current set of parameters fixed. So we fix our current thetas, and we apply, say, factor graph propagation to fill in probability distributions over our hidden variables. Okay? We don't fill in single values. We have to actually compute the sufficient statistics of the hidden variables. In the M step, we apply this complete data learning rule to the filled-in data. So essentially, in the M step, we apply this equation to re-estimate the parameters, except that instead of putting in the counts here, I put in the counts where I have them, and expected counts that I got from the E step, where I don't have the counts directly, but I have to fill them in by doing the message passing. Okay? Very intuitive. You fill in missing data, and then you re-estimate the parameters as if that was actually observed data, and you iterate the process. Okay, So that was maximum likelihood learning, but with hidden variables. Now let's go one step in another direction and consider Bayesian learning, where we are both going to consider the case with no hidden variables and the case with hidden variables. So here is Bayesian learning applied to any model. This is the very general kind of description of that. Let's apply it to the graphical models that I just described. So I think, did I skip those? Yeah, I think I skipped that, but we'll see it in a minute. So essentially, Bayesian learning applied to parameter learning in a graph. For when you have no missing data, it ends up being really, really simple to do this. So instead of computing these point estimates, what we need is to compute the distribution over the parameters given the observed data. That distribution will factor into distributions for each parameter given in each family. A family is a parent-child kind of combination. For each child, if you consider all its parents, you could call that a family. There are parameters associated with that. If we put Dirichlet priors on that, and your graph is discrete like this, then your posterior will be Dirichlet, and you can compute all of those analytically for every family in the graph separately. Okay. I won't go through that because I forgot to put the slide in. But we are also going to run out of time if I spend too much time on it. So here is a summary of parameter learning. We have maximum likelihood versus Bayesian learning. We have the case for complete or fully observed data versus incomplete or hidden or missing data. I told you about this. It was just calculating frequencies and renormalizing. When you have missing data, you can apply the EM algorithm. If you have complete data and you're doing Bayesian learning, you can update the Dirichlet distributions, as I was just hand-waving right now. It's as easy as calculating the frequencies. It's basically the same amount of computation. If you have incomplete data and you're trying to do Bayesian learning, then you have a slight problem, which is you have two kinds of unknowns. You're assuming that both your parameters are unknown, the thetas, and you have hidden variables x. Now, for any setting of the x, you can do the integral over the theta exactly, because under the assumptions I've been talking about here, your variables are all discrete, and the prior is Dirichlet, so we can do these Dirichlet integrals exactly. But there are exponentially many ways of filling in the hidden variables. So the exact posterior over the parameters in the Bayesian setting with hidden variables involves a mixture of exponentially many Dirichlet distributions. And we need to approximate that somehow, and these are where different approximation algorithms like Markov chain Monte Carlo or the Viterbi algorithm or variational Bayes can be used for doing this. Okay. So questions about that? Okay, so finally, let's talk about structure learning in graphs. So given you have some observations, can we learn the structure of the graphical model? In other words, can we learn which edges should we include and which edges should we not include? So the graph structure is simply just the set of edges in the graph. And there are two classes of structure learning algorithm that have been mostly used out there. There are constraint-based algorithms and score-based algorithms. In constraint-based learning, what we do is we're trying to figure out conditional independencies that hold in our data. That's the basic idea. Of course, for any finite amount of data, we don't know what exactly the conditional independence relationships should be, but we can do statistical tests for marginal and conditional independence. So we can do a bunch of statistical tests and we get a bunch of independent statements. And then we find graphs that are consistent with those independent statements. Okay? That's constraint-based learning. In score-based learning, we use a global score to score a particular graph structure with respect to the observed data. Like, for example, we could use BIC, which is an approximation to the marginal likelihood, or the Bayesian marginal likelihood itself exactly. And there what we're doing is we're doing model selection in a very large space of possible graphs by varying the structure of the graph and considering the score being the marginal likelihood for that graph given the observed data. It's exactly the same as the situation where I showed you with the MATLAB demo earlier today, where you're looking at different hypotheses, which are different numbers of clusters, and you have a fixed data set, and you're trying to figure out whether you have 6 clusters or 7 clusters. But here you would be figuring out whether this edge should be in here or not. Let's say. Questions about that? Let's look at that in a little bit more detail. Score-based learning. So sorry for that. Snuck in somehow. Essentially, we're just going to apply those rules to learning in graphical models. So let's imagine the situation with complete data, so we have no missing or hidden variables. So consider a graph with some structure M. You have discrete observed data D and parameters theta. We're going to assume Dirichlet priors on the parameters. Now, the marginal likelihood score is very easy to compute. The score for a particular graph is going to be the log probability of the data given the graph. Now, if I want to add the prior that's over here, I can add that to the score as well. But here's the simplest case. What is that? That's the log of the integral over the parameters of this probability here. Okay? Now, because my data is assumed to be discrete and I use Dirichlet priors, these integrals can be computed exactly and analytically. So the score for a particular graph structure is the sum over all I and j I think these correspond to, these correspond to nodes I in the graph and settings j of the child in the graph. And then there's a sum over k inside here with the settings of the parents of that child. Okay? So this score is something we can evaluate. It's all in terms of the log of the gamma function. The gamma function is just a generalization of the factorial function. Okay? So I do a bunch of calls to log gamma, a built-in function to MATLAB, and I compute a score for a particular graph. And the things I'm sticking in the log gammas are these alpha tildes, which are the priors, the hyperparameters of the prior for the Dirichlet, but incremented by the counts that I observed for particular settings of node I being in state J when its parents are in state K. Okay, that's this counts. Importantly, note that the score decomposes over the variables. So essentially, for every variable in the graph, I can evaluate what would happen to the score if I added a new parent or removed a parent. Okay? And this is great for search-based algorithms, which basically involve the following high-level description. You start with some graph structure. You consider a modification of a particular edge, add a particular edge or remove an edge, maybe invert an edge. And then you accept that modification if the score for the new graph is better than the score score for the previous graph. Okay? A simple, greedy optimization of structures is what this embodies. Of course, given that we can compute this score and it's a probabilistically meaningful quantity, we can actually do Bayesian inference in these graphs as well. So rather than accepting moves always when the probability increases, which is the greedy algorithm, we could sample over different structures, adding and removing edges. Well, what's the problem with this procedure? Anybody have any comments on this? Can you identify anything bad here? No? Yes? Okay, so one question is the graph structure identifiable? And it may not be, actually. That's a very good point, because you might have multiple, well, in this case, if you assume that the variables are all observed, then you don't have issues with hidden variables, but there might be identifiability issues. I haven't actually, in the fully observed case, there could still be identifiability issues because you might have symmetries in terms of A going to B versus B going to A, and you might never be able to tell those apart. Yeah. Another? Yeah.
I would suppose that you had problems that the more edges you introduced, the number of variables would grow a lot faster, and that would make them prone to overfitting.
Great. That's not a problem. Okay. So the point here is as you add more edges, it's true that the number of parameters increases. You're absolutely right up to that point. But the score here is a marginal likelihood score. So in this score, we've integrated out the parameters. We've computed the probability of the data given the model class. So by the same arguments I had with the polynomials example, there is an Occam's razor in effect here, which means that it's not the case necessarily that a more complicated graph would have higher marginal likelihood under this procedure. However, it might be the case that because the greedy procedure is trying to optimize in the space of graphs, it might find a peculiar graph, whether with too many or too few edges, that has overfit in the space, in the discrete space of possible graphs, but not because it has more parameters necessarily. So the answer to your question is quite subtle. Optimization in graph structures can overfit, but not necessarily in the way that you would think, that in the sense of preferring graphs with too many edges. It's tricky there. Yep.
For the Bayesian case, does it make sense to average two graphs?
So what does it mean to average graphs? Yeah, that's a good question. In the Bayesian case, you have a distribution over different graph structures, where some graphs, given the data, some graphs might be much, much more probable than other graphs. So that distribution gives you information about what's consistent with your data. But you have different graph structures, so you can't really average them naively because you don't get an acyclic graph if you just combine the edges. What does it mean to average graphs? I would argue you can't average graphs, okay, not in this setting. The only thing you can do is average the predictions of graphs, or average statistics that you could compute from those graphs. So for example, you could say, given my posterior over graphs, what is the probability that there is an edge between A and B? That quantity I can average. Or you could say, given my posterior over graphs, what is my prediction for this variable condition on these other variables? And then I could do belief propagation over all the graphs that are consistent, for example. Okay, yes? Cool.
So, isn't this a big sum to compute? Because as a discrete set, you need to consider each iteration of the parents for each.
This sum here, you mean?
Well, so you have that K sum, and then you can pull the sum over I inside, but then you have
Yeah, so in general, if I end up, let's talk about this sum here, this expression for the score. If I end up with a node which has many, many parents, okay, then it is true that these tables will have exponential many elements in it. So this procedure doesn't really work very well if I don't bound the maximum number of parents that a node can have. That's a good point. That's quite subtle, actually. But here's another simpler problem with this. The problem is the space of graphs is huge. For n nodes, somebody here must know, it's super exponential in n, the number of directed graphs I could write down. So, greedy search just might not find a good graph. Or even Bayesian inference using sampling might be sampling for a long time and not find anything interesting. Okay. But there are, I'm not describing the absolute state of the art. There are some clever things you can do that reduce the sampling space, like sampling over orderings of variables, integrating out all possible structures for a given ordering. There's a very elegant paper doing that. Okay. So now let's complete this structure learning square by talking about structure learning when you have hidden variables or missing variables. So now what we want is we want to compute our score as before, which is the marginal likelihood. But the annoying thing is that we need to both integrate over the parameters and sum over the hidden variables. And that's generally intractable. But there is a widely used algorithm called the Bayesian structural EM algorithm, which can be considered an approximation to computing this intractable score that will be able to learn graph structures with hidden or missing variables. Okay? The basic idea is it's kind of inspired by the EM algorithm. You compute map parameters for a current model M using the EM algorithm. So you have a current graph structure, you compute your map parameters, and then you do the E step to find your hidden distributions over the hidden variables, which might involve some message passing or belief propagation or whatever. And then for a small number of candidate structures, you compute or approximate this score, which is an approximation to the actual score that you want to compute, where you fix the distribution over the hidden variables to be the one computed in this step, and you then evaluate the exact score, assuming complete data essentially here. And then you pick the model with the highest score, and you iterate this procedure. So I showed you variational Bayesian learning for the mixture model case with the demo before. Now I just want to show you that variational Bayesian learning can be applied to learning graph structures as well with hidden variables. So here's a very tiny toy problem where I have 4 observed variables, up to 2 hidden variables, and for graphs like this, I can enumerate all the structures. I have 136 possible structures with 2 latent variables and 4 conditionally independent observed variables. So it's a small enough space I can enumerate all the graphs, and then I can analyze the behavior of different algorithms. So here's how we're going to do this. We're going to compute the different scores for each of the 136 structures for 20 varying sized data sets. This is what makes it interesting. So we're going to go from 10 data points, 10 observations of these 4 variables, up to 10,000, okay, in this particular sequence. And we're going to compare each method is, this is BIC, which I described before. This is variational Bayes. And then there is an annealed importance sampling method, a sampling method that is trying to compute the exact scores as best it can. Just for comparison, for each graph, back when we did this comparison, BIC took 1.5 seconds, variational Bayes took 4 seconds, and annealed importance sampling took 400 seconds. Okay? So the sampling method took a lot longer. Here's the sort of results that we get out of this. And I really like looking at results of this kind because it gives you some very interesting information. So on this axis, what we have is a success rate at selecting the true structure, or here the posterior probability that the true structure is greater than the baseline, which is 1/136. So 2 different ways of looking at this. And then what you get on this axis is a number of data points. And I think this kind of picture characterizes many, many learning problems. So if I have 10 data points, I can't learn anything. Okay, no matter what method I use, all the methods have a success rate of 0. On the other hand, when I have 10,000 data points, all the methods are doing reasonably well. So the way we tell learning algorithms apart, I would say, is by evaluating how they do on varying size data sets. And here what we see is these nice curves that are averages over 100 parameter draws, where essentially what happens is that the variational Bayesian procedure kind of goes up at asymptotes first, and then there is a method called Cheeseman-Stutz. There's a method called, there are 2 variants of BIC, and both of those do worse than these 2. So a similar pattern is occurring here with some anomalies right at the beginning, which we can ignore actually. The point here is that there is a sweet spot for learning. Okay? In any learning problem, if you have massive amounts of data, any reasonable algorithm will do well. So pick a cheap one. If you have tiny amounts of data, nothing can learn the structure there. So just forget about it. If you're in the sweet spot, then the improvement that you get in performance for different algorithms translates into effective number of data points. Okay? So what we get is a modest, maybe, you know, you're going maybe from around 1,000 data points as compared to BIC, which could be 2,000, 3,000 data points or something like that. Okay, so you know, if we slice this right in the middle where the action is happening, then variational Bayes can do as well with 1,000 data points as BIC did with 3,000 data points. Okay, that's a natural way of thinking about, in this particular case, what is the particular gain that we get from using a better inference algorithm. And we can do this sort of exercise for all sorts of things. So here is just another interesting plot where we're going to look at the marginal likelihood inferring a particular large graph, in this case, trying to compute the marginal likelihood with a sampling method like annealed importance sampling, and with the variational Bayesian method, which gives you a lower bound on the marginal likelihood, and with BIC, which in this case also happens to give a lower bound, but is not guaranteed to give you a lower bound. Okay, so this is also an interesting plot. What's plotted on this axis is the, on a log scale, how long I run my sampling algorithm. So essentially what we have here in this graph structure learning scenario is that I need to collect about 10,000 samples from annealed importance sampling so that I'm actually above the lower bound on the marginal likelihood that I know I could have computed with VB. And then if I collect something like you know, several thousand samples, I get to see that the VB lower bound is that much worse than say that's the true value there. There's one way to see how tight are these variational lower bounds in situations where I can spend a lot of computer time computing the actual value as accurately as possible. Any questions about this? Yes?
So it's very interesting to see these sample complexities for the different methods. Do you have a feeling also for how constraint-based methods will work with the different independence testing?
I hadn't done the same experiment. I think it would be very interesting. I mean, this experimental procedure is very easy to do. We just Matt Beal and I happen to be interested in score-based methods. So we essentially evaluated, forgetting about the search algorithm, we enumerate all the structures and we say, what's the better score? You know, are these scores uniformly better than other ones? We were able to prove that the variational Bayesian score is always going to be better than Cheeseman-Stutz. In fact, Cheeseman-Stutz is a lower bound on the marginal likelihood, which is guaranteed to be less than or equal to the variational Bayes. But you know, you could interpret this either as great results, like wow, we are, you know, a third and fewer samplers, you know, data points that we need in the hotspot here. Or you could say all the gains are modest. You know, essentially, if you have some problems, it doesn't matter. If you have other problems, it also doesn't matter. Right. But it would be very interesting to put constraint-based methods on the same kinds of plots. Yeah. Okay, so I'm almost done, and I'm almost out of time. So I just want to touch on the last few points that I wanted to discuss as kind of more advanced topics. So one of them is how many latent variables should you have in a graph structure with hidden variables. So consider a particular form of graph where I have all my observed variables here, and I have all my hidden variables here, and I don't know how many hidden variables to use. Well, we can actually use some of the Bayesian nonparametric ideas that Peter Orbans and Dylan were just talking about to learn the structure of graphs with hidden variables. The basic idea here is I'm going to assume potentially infinitely many hidden variables, and then I'm going to say of this pool of infinitely many variables, how many do I need to connect to my observed data? And so this is in joint work with Frank Wood and Tom Griffiths. We did some work where we looked at nonparametric Bayesian learning of graphs with these hidden causes for some observed data. And I won't go into the details of it, except that we used as a prior on the graph structure. The graph structure can be thought of as a binary matrix, which gives you the adjacency between hidden variables and observed variables. And we used an Indian buffet process as a prior on the graph structure because it had some reasonable properties which allowed us to do inference when we have infinitely many hidden variables. So I won't really talk about that. We just implemented a sampler which would sample on these hidden variable models. And for some particular data, you could get some structure out where you could then try to interpret what these hidden variables actually mean in terms of the observed data. I want to mention this very, very interesting topic of causality, just in one slide, which is to say that directed graphical models are statements about conditional independence between variables, but they can also be interpreted with some caution as a representational tool for causal relationships. So causal relationships are clearly fundamental to human cognition and also to all of scientific discovery. And you know, even when we have situations where we have identical independence relationships, the causal relationships are very different. They encode very different things. So for example, if I have a variable smoking going to yellow teeth, if that's representing a causal relationship, that's very different than yellow teeth going to smoking. because yellow teeth going to smoking would make a prediction. If you paint somebody's teeth yellow, then they will start smoking, for example. Okay? And we can test those sorts of predictions. The key idea in the literature on causality is to distinguish between what happens to the probability distribution if I merely passively observe states of a set of variables, as opposed to what happens when I intervene by manipulating one of the variables. And that's the sort of idea of the do calculus, where I distinguish between merely observing that y took on the value little y to what would happen if I painted somebody's teeth yellow. Okay, so these probabilities would end up being different. One of the key problems with causal learning is identifying hidden common causes. Because if you have a hidden common cause, you don't know if A caused B, B caused A, or there was something C that jointly caused the relationship between A and B. I won't really say much more than that, but I do want to advertise. Bernard's been doing some really interesting work on this with Dominic Jansing and a bunch of other people with a very different view on causal learning than what's been done in the classical statistics literature. Okay, so, the graphs fell off the edge of the page. Okay. So I think I'm almost done. So I talked about directed graphs. If we want to extend structure learning and parameter learning to undirected graphs, then undirected graphs, things like direct representation of the distribution as a factor graph, let's say, the problem is when we write down any undirected model of this kind, then we always end up with a global normalizing constant. So this z of theta is a normalizing constant that involves summing all of the factors over all the variables. Now, in a general undirected graph, computing the normalizing constant is computationally intractable. So what am I talking about? Sorry, just to give some terminological links to people. When I talk about undirected graphs, I also mean Markov random fields, conditional random fields, Ising models, a lot of these things that you may be familiar with. Okay, so the problem is the normalizing constant. And maximum likelihood learning is intractable in these models, and Bayesian scoring of structures is also intractable. But there is a body of work by Ian Murray, myself, and others where we've been trying to apply some of the approximate inference methods to learning of undirected graphical structures as well. So finally, I talked about graphical models. If you want to see some very impressive scaled up applications of graphical models, then there are a few very nice case studies. The folks at Microsoft Research in Cambridge are particularly good at scaling up graphical model inference to very, very large situations. There are two examples of this. One of them is on the Xbox Live. So who plays Xbox here? Okay. Admit to it, the rest are too shy. Okay. So if you play Xbox in a network setting on Xbox Live, then you're matched up to other players for different games. The way that's done is that the Microsoft kind of server has a hidden variable for what's your skill level at that game. So based on your performance in any game, it is doing belief propagation to figure out your skill level. This can be quite complicated if you're playing a team game where there are multiple players with different skills and you win or lose. It has to attribute the win or loss to different people. It uses belief propagation to do all of that. And then it matches you up to other players or other teams with similar skills, so you all enjoy playing as much as possible and keep your subscription or whatever going. So interesting thing about this is that this is an instance of belief propagation happening at a global scale continuously, with millions and millions of games and players around the world, messages being passed around 24 hours a day. So if you're a big company like Microsoft and you have a few good programmers, you can take things like belief propagation and scale them up to very, very massive data sets if you want. Similarly for ad predictor, which tries to predict who's going to click on which ad on the Bing web pages. That's also belief propagation on a big graph. Okay, so that's it. I gave you kind of an overview of graphical models, where I divided it into inference, parameter learning, and structure learning. And then I mentioned some more advanced topics like undirected graphs, causality, and sort of scalability, which are really state-of-the-art issues here. Okay, great, thanks.